Welcome back to the workshop for our last video on conditional distributions. And in this last video, what we actually want to talk about are the independence of random variables. So the idea in this section, the idea of the independence of random variables, is the same as what we were talking about for events previously. Independence of two events was, or the definition, right? Two events are independent if the probability of both of them occurring is equal to the probability, the product of the probabilities of the individual events occurring. So we find that it's essentially exactly the same thing here, right? Because kind of like what we identified in the intro video to this section, and even in the intro to the previous couple sections, I believe, is that we can look at particular events as values for a discrete random variable. So that kind of bridges the gap and brings us to the idea of our random variables. Okay, so let's take a look at our notes and see what this definition says and take a look at an example. So the independence of discrete random variables is the particular definition that's given. So if this function is the value of the joint probability distribution of the discrete random variables x1 through xn at particular values, and f sub I of x sub I is the value of the marginal distribution of x sub I, right? So you can take I being equal to 1, 2, 3, 4, all the way up to n. Then the n random variables are independent if and only if f of x1, x2, all the way up to xn is equal to f1 times x1, f of x, f1 of x1 times f2 of x2 times f3 of x3, all the way up to fn of xn. Now I believe that this is not the complete definition. I'm thinking maybe I forgot to copy something here, because much like when we talked about the independence of multiple or many events, we had to consider the probability of all of them together, every pair, every triplet, all the way up to the all n events. Okay, so we should also actually have f of x1, x2 is equal to f1 of x1 times f2 of x2, and so on. So let me double check how they phrase that here. Just one moment. Well, of course, that moment was very brief for you, but I took a look at the textbook, and it actually is just this one particular equality that we need in order to have that independence. So it's a little bit interesting. And now that I think about it, though, what you'll find, one of the things that you want to investigate, if I recall, it's either in the textbook or it might be in the assignment, is identifying that for a function that has 3 continuous random variables, that 2 of them are independent and the other 2 are independent, but the 3 of them are not independent, if I recall. So that's what must be what I'm thinking of here. So to obtain the definition of independence for the continuous random variables, what's convenient is in the definition that we just gave, we just have to consider the replacement of distribution becomes density, right? Distribution versus density, discrete versus continuous, that's it. Of course, in either case, we do want to only consider the values of the random variables that they can actually take on, and that makes sense. So we're going to consider the continuous case where we have continuous random variables x1 and x2, and we're going to assume that they're independent from one another, and we have their individual density functions given here in this example. Okay, so there's their individual density functions. And we want to find the probability that x squared plus y squared is between 1 and 3. So the first thing, and actually here, this correction I think has been made on your notes, but it should be between 1 and 9. Try to keep numbers relatively simple here, make things easy on us. And essentially what we're looking to do is we want to integrate the density function over the region that satisfies this. So first of all, what is the density function that we're looking at here? So f of x1, x2 is going to be the product f1 of x1 times f2 of x2. And x1 takes on these values between -4 and 5, and f2 of x2 takes on this value for values, x2 value between 0 and 4. So we've got 1/9 times 1/4 is 1/36, the product of the two functions, for x1 values here and x2 values here. So we've got -4 for x1 up to 5, and 0 for x2 up to 4. And then, of course, it's taking on the value 0 otherwise. Excellent. So what we want to do next is we want to recognize that all we're doing is integrating this function given here over the particular region of interest, right? The points that satisfy this inequality. So first, let's start by looking at what region the function is defined on. So if we call this axis x1 and this axis x2, then we're ranging from 0 to 4 and from -4 to 5. Cut it in half and half and half, so 0, 1, 2, 3, 4. And from -4 to 5, 0 should be somewhere around here. Go like that to split it into -4, 3, 2, 1, 0. And then 1, 2, 3, 4, 5. Excellent. So that looks pretty good. From here, I want to, again, recognize that 0 is right there. But then I want to recognize what points satisfy this inequality. So if I look at the equalities, 1 is equal to x squared plus y squared. I'm looking at the unit circle, but of course I'm looking at x2 values that are greater than 1 or greater than 0. And then if I look at the equality, x squared plus y squared is equal to 9, I'd be looking at the values from -3, be looking at the, not the unit circle, but the circle with radius 3. So I'd be looking at that, which means that the area inside of that is our region of integration. So this stuff here is our region of integration. But is that really the easiest way to think about it? Does it turn out to be super convenient to try and integrate over this particular region? No, not at all, to be honest. That could be a little bit challenging. So we want to calculate things in a little bit easier way. So what I want to do is I want to recognize that if I want to calculate the probability of the area in this, if I want to calculate the probability that our x and y values will take on those values inside the red region, I'm integrating over that region, but I can do that, right? Remember that the integral from a to b can be written as the integral from a to c plus the integral from c to b. So essentially what I'm telling you there is that we can integrate over this entire region, including this area here, and that would be our integral from a to b, and I can split it up into the two pieces, right? So fundamentally, this is the concept that I'm using here. And what I'm going to do is I'm going to calculate the integral of this entire region, including that additional half circle. And then I'm going to calculate the area of that smaller half circle. So all I'm doing is computing or calculating the integrals over those two semicircle regions. and then I'm going to subtract them. So I take the probability of the larger, take away the probability of the smaller, and I'm left with the probability that our x and y values are within the red region. Okay, pretty straightforward. So that just leaves me to find ways that I can represent. Right, I want to integrate. Let's see here. I think I can write this as, yeah, okay. So I want to integrate over x1 first. No, x2 first. Yep, there we go. I want to integrate over x2 first because what's going to happen is it's going to be really easy for us to integrate over these rectangles, because I can find an equation for that outer line, and I can find an equation for that inner line. So I can integrate from 0 to this value here because I can find that. And then I can integrate from -3 to 3. And I can integrate over this area and then integrate from -1 to 1. Okay, making the integrals relatively easy. So the equation of the outer line is essentially given for x1 squared plus x2 squared is equal to 9, and this is for x2 being greater than 0. But since x2 is greater than 0, it becomes extremely convenient then to solve for x2, and we can get that x2 is equal to the square root of 9 minus x1 squared. So that's going to give us the values up here. Since I took the square root, I'm looking at the positive values. So I am looking at exactly this line, and there's nothing to worry about. Okay. All right. So we have that, and then then the equation of the inner. I suppose I should call them circles. Outer circle and the inner circle is, of course, x1 squared plus x2 squared is equal to 1, radius 1 there. So similarly, x2 on that one is equal to the square root of 1 minus x1 squared. So with that, the larger region, I can integrate from 0 to square root of 9 minus x1 squared. And then I can integral over the variable x1 from -3 to +3. So the probability in particular that x squared plus y squared is less than 9 is given as the integral from -3 to 3 of the integral from 0 to square root 9 minus x1 squared. And we're integrating the function f of x1, x2, which is 1 over 36. 1 over 36, so it's just a constant. That's very convenient. Integrating with respect to x2 first, and then x1. All right, from here, this integral, right, it's a constant. So when I could pull that all the way out to begin with. So the integral of the constant x dx2 is going to be the constant times x2. Plug in this minus plug in that leaves us with 136 times the square root of 9 minus x1 squared dx1. Excellent. So this looks pretty good, but maybe not quite as good as we'd really like it to, because holy cow, how do you calculate that? Well, this actually requires, so this is why calculus, well, not only is calculus 3 a prereq because we have the multiple integration, but we also need calculus 2 in order to be able to perform this integration. This requires some supplemental integration techniques that, as far as CUAA goes, we would see in chapter 8 of the text that we use here. So in this case, it actually works out that we need to do a trigonometric substitution. So we say, all right, here's theta, and since we have 9 minus x1 squared, it works out easiest, right? Noticing that it's 9 minus, it works out easiest for us to say that, hey, that would work out for us to call this x1 and this 3, because then this side would be the square root of 9 minus x1 squared. So if we wanted to identify x1 is actually equal to 3 times the cosine of theta, which you could find by saying, hey, 3 times the sine of theta. 3 times the sine of theta. There we go. Which you could find out by saying, hey, what's a trigonometric function that relates x1 and 3? Oh, hey, sine does. Cool. Sine of theta is x1 divided by 3, so x1 is equal to 3 times sine theta. And that gives us dx1 is equal to 3 times cosine theta d theta. And we can make those substitutions here. But one additional thing that we should recognize is that when x1 is equal to 3, theta is equal to pi over 2. And when x1 is equal to negative 3, theta is equal to negative pi over 2. So that way we can replace our integration bounds as well. All right, so this is going to be equal to the integral from negative pi over 2 to pi over 2 of 1/36 times 3, right, once we perform this, 9 minus, well, actually, let's just plug it in so that way we can see what's going on here. I'm going to have the square root of 9 minus x1 squared is going to be 9 sine squared theta, and then we have cosine, actually 3 cosine theta d theta. So once we have that, we can pull out the 9 from both of these, and the square root of 9 is 3, so 3 times 3 is 9. 9 divided by 36 is 1/4. We're left with 1 minus sine squared underneath the radical. So it's still the integral from negative pi over 2 to pi over 2. We're left with 1 minus sine squared underneath the radical. 1 minus sine squared is cosine squared. Square root of cosine squared is cosine. So this is cosine theta times cosine theta. So it's cosine squared d theta. All right. Now, in order to find this, we have to use our techniques for finding trigonometric integrals. So we actually have to rewrite this without the square, which we can do. So this is 1/4 times the integral of, integral from negative pi over 2 to pi over 2 of 1 plus cosine 2 theta divided by 2 d theta. And then we can evaluate that. So that's 1/4 times, let's see here, 1/2 theta. Integral of cosine is sine. So plus 1/4 sine theta, because we already have the factor of 1/2. And then, and that should be sine 2 theta. Evaluated from negative pi over 2 to pi over 2. But it's 1/4 because we have to account for the 2 inside the sine function. What I mean by that is if we were to take the derivative of this, it'd be the derivative of sine is cosine, the derivative of 2 theta is 2, so it would be cosine 2 theta times 2, and we need 1/2. Okay, so 1/4 times 1/2 gives us the 1/2. All right, from there I can evaluate this as 1/4 times, let's see here, pi over 2 times 1/2 is pi over 4. Sine of 2 times pi over 2 is sine of pi, which is 0, so plus 0. And then minus, plug in negative pi over 2, so negative pi over 4. And then minus 0. 1/4, well, pi over 4 plus pi over 4 is pi over 2. 1/4 of pi over 2 is pi over 8. All right, So holy cow, that was a lot of work to calculate that one integral, which is fine. I would like to point out, since we're working with a circle here, we could actually rewrite things in terms of polar coordinates. But if you did that, it would become an incredibly easy integral, even easier than what we've done here. Very easy, because we wouldn't have the weird integration bounds. It would just be an integral from 0 to pi and 0 to pi. Much easier. Yeah. Well, sorry, it'd be the integral from 1 to 3 and 0 to pi. So you could find that area specifically without the subtraction. Be very easy. Without getting into polar coordinates, this is what we have to do. So similarly, I would encourage you to calculate this integral with the probability that x squared plus y squared is less than 1 turns out to be pi over 72. So when I perform this subtraction to find the probability I'm interested in, I need this in terms of a fraction over 72. So multiply by 9 to get 9 pi over 72, which is going to give us the result that we're interested in. So the probability that our x and y values satisfy this equation is equal to the 9 pi over 72, the larger probability, minus this probability, which is 8 pi over 72, or simply pi over 9. Whew. All right. So again, you could have also used Mathematica or some other computer algebra system to help you evaluate that integral. But this is the techniques that would be required otherwise. And will you see an example like this in your homework? Hey, maybe. And if not there, maybe on the exam. So keep that in mind. If you have any questions or concerns, of course, get a hold of me. But I'll see you guys soon back in the workshop, moving on to our next section, or into our next chapter, even into chapter 4. So you guys have a great day. Thank you for your time and attention. I'll see you later back in the workshop.